So we're going to introduce exponential functions here. I would suggest if you're taking notes to write everything in the orange for sure. This fourth question we're going to address on a different slide. So here are the two ways you're initially going to see exponential functions. Y equals AB raised to the x, or y equals C times the quantity 1 plus r raised to the t. Now these formulas really mean the same thing. A here is the initial amount. This is what you started with, say in an experiment. Or if you went to the bank and you opened an account, this is the amount of money that you started with. C is in the same place. It's the same thing. This is the amount you started with given a situation. This is also the y-intercept. So we're going to graph it in a minute, and that will be important because it's the y-intercept. All right, B is the growth factor. Could also be the decay factor. So we'll write growth if things are growing, getting bigger, or if it's getting smaller in our situation, this is decay factor. Now, B is in the same place as 1 plus r, so it's this entire thing that would be B. The r by itself would be the growth or decay rate. That's the average rate at which it's growing or decaying. Now, x and t are in the same place. This will be time in a lot of instances, which could be measured in days, hours, seconds. It's going to vary. This could also be, we'll see in an M&M or penny experiment, this is the number of trials we did. How many times we dumped out pennies from a cup is what we're going to do this year. So it could be time, the number of trials, how often you did something. Now, looking at two equations filled in with numbers here, we're going to determine is it growth or decay, what is the A, the B, and so on. So looking at this one first, it looks like A is equal to 12. So whatever the situation is, I started with 12, maybe 12 pennies, and I wanted to watch it grow. The B value here, this is B equals 0.95. This is the growth factor. And because B is smaller than 1, I'm going to say things are decaying. Things are getting smaller in this situation. Now we said 1 plus r was the same, or 1 minus r, since things are decaying. I don't really need the parentheses here. We said that B is 0.95, and that equals 1 minus r. If I want to use the factor to figure out the rate at which things are decreasing, I would just say 1 minus what is 0.95, and that would mean r is 0.05. So there's the rate at which things are decreasing. If I wanted to get that as a percent, I would just multiply it times 100, and that means things are decreasing at a rate of 5%. And then x here just represents the time how often something has happened. Let's look at that in this one, where A is 0.25. So maybe I put a quarter in my bank account and wanted to see it grow. So there's A. Here's B. B is equal to 2. So what does that mean in terms of r? What's the rate at which it's growing? So if B equals 1 plus r, I'm calling it plus this time, it's growth, because B is bigger than 1. B is 2, bigger than 1. That means things are growing. So what would r be in this case if B was 2? 1 plus what is 2? Well, that means r is equal to 1. Multiply it times 100. That means your rate is 100% growth. So things are doubling in this situation. So I go back to my bank and find that I have 50 cents, then maybe $1, and so on. Now the most common, or I guess you could call them the parent functions of this situation that you're going to see, y equals 2 to the x, and you may also see y equals 10 to the x. Now we don't see A and B. A, by the way, is 1 if you don't see it. So A is 1, B is 2. So the rate at which things are growing isn't that fast. Whereas 10 is a little bit higher if we put the 1 for the A there times 10 to the x. 10 is a bigger rate, so this one would be growing a lot faster, growing for both situations because 2 and 10 are bigger than 1. All right, so let's look at some graphs for that. Here it is. This top one is y equals 2 to the x. Bottom one is 10 to the x. Those are the most common we're going to see. Now we said the 1 is there even though you don't see it. This is 1 times 2 or 1 times 10 raised to the x. And look, that's the y-intercept. So we see that it crosses the y-axis at 1 for both of these. Now I said 10 was a faster rate than 2. So look at how this graph looks. It's really, really steep, bigger, faster, steeper. The bigger the b value, the faster things are happening. versus 2, it's not happening as quickly, but it still is growing. Now this just shows you a table of values here that they use to get the dots to draw this line. If we were talking domain and range, we haven't done that in a while. Domain, you'll travel to the left and to the right. If I travel to the left on this line, I'll see that it goes left forever. As I travel to the right, it's going to appear that it goes up, but I tell my brain I'm moving to the right. That also will go forever. So that would be negative infinity to positive infinity, otherwise known as all real numbers. Now this graph, 10 to the x, does the same, left forever, right forever. So that domain is also all real numbers. Looking at the range, now we can tell our brain we're going up and down. It does go up forever. Both of these do that, goes up forever. But then when we're going down, it starts to go down, and it looks like it's going left, and it looks like something here is stopping us on both of these, right? It doesn't appear that it's going down any further. And what's happening is there's something called an asymptote there. It's right on the x-axis for both of these. Now, in later lessons, we'll move this around. We'll figure out how to identify where that asymptote is. But it's like this imaginary line that's repelling it, and it's not allowing it to go down. Now, it is still continuing to go down, just at a very slow rate here. It looks like it's touching the x-axis, but it never actually touches it because it's being repelled by the asymptote. You'll see these numbers get smaller and smaller and smaller. This table shows a good example of that. 0.5, 0.25. It's trying to get to 0, but it can't. Gets down to 0.0625. The next one might be 0.00 something, 0.000 something. Keeps getting smaller and smaller, closer to 0, but never actually gets there. And this is showing the same thing, but in fraction form. So there's an asymptote stopping it from going below the x-axis and stopping it from reaching 0. So the range would be y, because range is the y, is greater than 0, not equal to 0. It never gets there. Same for this one. Whoops, I forgot the y. Y is always greater than 0. It's always above the x-axis. All right, so this talked about what question number 4 in the original slide talked about. What about if we had a min or a max over the interval, and they said the interval was -2 to 1. I don't know if you can see it, but there's a red line here. They're just saying you have to stop here, forget about the graph outside of this interval, and only focus in here. What's your lowest point within this interval? What's your highest point within the interval? So the way to get that, if you have 2 to the x, is you're just going to insert the numbers that they tell you. 2 to the -2, see what you get there. 2 to the 1, see what you get there. For this one, they've calculated this. This one would be 1/4. And for the other one, they say that would be 2. So 1/4 is the smaller value. Call that the min. And then we'll call that one the max. Same thing for 10 to the x. They plugged in -2. They got 1/100. So there's the min for that one. That's the lowest point. And then if you plug in 10 to the 1 power, that's 10. So there's the max within that interval. That's all that means. We'll talk more about that if we need it. So here we are. We're going to graph a couple of them. This is the way it works in a nutshell. Here's the a value. That's my initial amount. That's also the y-intercept. So we're going to put a dot where 4 is. Now 2 isn't a very fast rate. We said that earlier. It's slow going. We're going to draw an asymptote here on the x-axis, so we're not allowed to go past this point. So it's going to be repelled here, and then it's going to slowly grow, and then as we hit this point, maybe things speed up and they start to increase growth because, again, the b value is bigger than 1. What if that was smaller than 1? What if it was decay? So the way that works is a is still 4, so I'm going to put a y-intercept of 4. But now the b value is less than 1, so this line should be going down. Again, we still have the asymptote here that we're not allowed to cross over. We're being repelled by it. So we're going to start way up here and then start to decrease. That's kind of a bad looking line, but eventually the asymptote repels us and we start to turn to the other side. So this should be more curved. Maybe it looks something more like that. So that is how you graph it, more or less. Now, this starts to, the exponential graphs start to reflect like disease and transmission of disease, viruses, germs, whatever. And so I'm showing you this picture of what this teacher did. I found this online showing mold growing on bread in different instances. So maybe this is disease spreading. Now, I don't know that mold actually follows any kind of exponential pattern, but if it did, let's say, here's what the teacher did. Took a piece of bread, it's fresh, it's untouched, and the teacher just threw this in a bag and hung it up. And so there's no real mold. I think they let it sit for, say, 7 to 10 days. They took another piece of bread. They had a student come up with dirty hands, had not been washed, and they said, I need you to touch this bread and then put it in the bag for me and hang it up. And over 7 to 10 days, some mold grew. They had another student wash their hands. Maybe it was the same student with soap and water, and then they had him come touch the third piece of bread. You can kind of see some mold on this one, but not a lot. Put it in there. And these were all done at the same time. One student had to clean their hands with sanitizer and touch the bread, put it in the bag. And then finally, the teacher took one of the pieces of bread, grabbed a Chromebook that all the students had been using for the week, rubbed the bread all over it. So no students touched it. It touched the computer instead that had germs on it, and then that went in. And this is what happened over the course of 7 to 10 days. If this did follow an exponential pattern, I think we would see that there's not a lot of growth here, right? If this one followed it, boy, there's a lot of mold here. So over the 7 to 10 days, this thing started growing faster and faster and faster. Soap and water had a little bit, so it's going to be more than if it was untouched, right? But it's not going to grow very quickly, just a little bit higher than this other one. Hand sanitizer, not as bad as dirty hands, right? But boy, this goes to show soap and water must be better than hand sanitizer. This one grew at a little faster rate, but not as bad, right, as the dirty hands. And then, ooh, nasty, look at this one. This is why you should disinfect your Chromebook, wash your hands all the time before and after. This one just spikes, clear up, right? And so the growth was happening really fast. So the steeper this line, the faster the growth happened here. You want to wash your hands, is what I guess with soap and water. The moral of that story is so that you don't spread germs or get it yourself. All right, so a couple years ago, I showed this graph. We had measles basically eradicated. That means it was basically gone. People were getting their vaccines, and then they stopped for whatever reason. And so the measles came back into play in the United States. In 2016, we had 86 cases. In 2017, that spread to 120 cases. In 2018, it jumped to 372. When I showed this to my students in 2019, we were in March, and this was only at 268 cases. I asked them to predict, what do you think is going to happen? Where is this going to be at? Do you think it'll stay there? Will it grow bigger? You can kind of already see, right, the exponential growth here, that curve taking off. This is what all disease and germs tends to follow until you get it under control. And at any rate, looky here, we looked at it in 2020 when it was over with, and boom, 375 shot up pretty quick. So this thing starts to get out of hand quickly if you don't get it under control. Let's look at a situation. We had the Ebola outbreak in Africa in 2014. All these lines just show the different areas. What is this? Guinea, Nigeria, Sierra Leone, some total cases, right? So the total is the big steep line, but no matter where they measured it, it always followed this exponential growth, right? And so we sent Doctors Without Borders there because we knew we had to help stop this before it got out of control. It was an epidemic, meaning it was just kind of local there in Africa, but we didn't want anything like this to jump over, like somebody gets on a plane, right? I know we had a couple of doctors that went to help and they got on a plane and came back to America. We had to isolate them, right? We didn't want this to then spread in America or other countries, kind of like coronavirus did, right? Started in China, somebody got on a plane and then it just spread and became a pandemic, which meant it was worldwide. So we got to get this under control, whatever the situation, before it starts to grow too quickly, because then this thing takes off, which we saw in the moldy bread. So here we are. We had a lockdown somewhere in March, must be over here. We got May, June, July, August. And these were some simulations that they did in Bexar County, a county in Texas. We were trying to see what would happen if everybody just went about their normal business. Well, this line here with the sharp curve, here's the exponential curve going up before the cases eventually start to go back down and people get healthier. If 100% of the population just went out and we didn't have a lockdown, this might be the simulation. We'd very quickly, before even getting to June, get to 200,000 cases. And why would this be bad? Well, because we'd start spreading the virus, whether we knew it or not, knew that we had it or not. And then somebody who is elderly or immune compromised might get sick, and they might get it, and then, what could happen? They could die. So that's the situation of how quickly we would spread this thing if nobody went on lockdown. If some people, 50%, went on a lockdown, this wouldn't grow as quickly. You can still see the exponential curve, but this one doesn't even get to 100,000 deaths cases, my bad, until maybe mid-July. And then if everybody, well, almost everybody, 20% of the population returned to normal, acted like nothing was happening, and 80% of us stayed home, wore a mask, did whatever precautions we did, then look how slow this curve is, and it doesn't really grow, and we keep it under control. So we're coming up with these models because, one, we didn't want it to spread. We didn't want anyone to die that didn't need to. But at the same time, if we went to total lockdown, right, the economy might shut down. It wouldn't sustain itself. People lose jobs. We happen to see and know now there was coin shortages and all kinds of bad things. Toilet paper was gone from the shelves. So we had to try to figure out which model was best for us to balance. Now, as we start to let this play out and we start to see how many cases actually panned out, that's what all these dots are, and we're getting into June 20th here, we can tell, based on which model we did, how many cases, and we're able to adjust to this model now as to what we need to do moving forward. Do we stay in lockdown? Do we let more people go out and about? Do we close down bars and restaurants, schools? What are we going to do? And we can start to project how many cases we're going to see in the future, into July, say. Now, here is another model. And these actually are models that happen. This is what we were trying to see. This one kind of looks like maybe we followed this blue one, I guess. So some of us went out and about, and some of us didn't. And this one, I can't see the months down below, but this one came from the governor of Texas. He used this one. There's that exponential curve. To decide once it got to 20% positive cases, that's when he said 25% capacity for restaurants and bars. And then as cases go back down, right, we get on the other side of the hump, we can start to open up with the mayor locally or the governor, whoever's going to make these decisions for us. So moldy bread, going back to that, one of the things we're worried about now is the transmissivity rate. That's how quickly things spread of mutated viruses, right? So now we have what they call the variants. And the variants are a little bit stronger. Our immune system may not be able to fight it, even though it fought back the first coronavirus we were exposed to. And so some are worse than others, right? So some variants we should be more afraid of. Maybe the UK one is a really scary one. It's like dirty hands. It spreads faster and it's a steeper line. Maybe the Brazil one is like hand sanitizer. It's not quite as bad as dirty hands, but it's worse than, if we were cleaning our hands. We fought the coronavirus the first time, and soap and water is our immune system. Or maybe South Africa, there's got really bad because of medical marginalization or something, and this is really bad. We should be scared, and this is going to spread quickly, so we all need to get vaccinated if you're willing to do that. Now I'm just kind of throwing things out there for you to understand what's happening in the media. I don't really want to push anything on you, but this also works with money. Okay, I had to remind myself what was behind there. So this guy is saying, more or less, if you want to read this, that instead of spending $5 on a coffee every day at Starbucks, what if you invested $5 into Starbucks stock every day? And if you did that over time, I think these are in years, up to 50 years, this is what would happen. Your money would eventually grow, and instead of wasting your money in 50 years, you would have $800,000. Usually what happens if you put this into a bank account or a stock market, you get interest, you get dividends. Dividends are just the profit that the company sees, and then you reinvest that profit into the company, and then your money starts to grow exponentially, right? It compounds and grows faster. Same with a bank account. When you get interest, you get money for leaving it in there. And here's an example of Jack and Jill investing their money, but they do it at two different times. Jack does it at an early age. I can't see. I think he was 25 right here. And Jill does it at the age of 35. So Jill waits a little bit longer, but both of theirs grows exponentially. The problem is Jill waited 10 years later, and Jill continues to put in $200 every month, never stops putting in $200, whereas Jack starts putting in $200 a month, but then stops right here at the age of 35 when Jill starts. And Jack never actually puts any money in again after this, But notice his money continues to grow and is always above Jill's. So in the end, Jack only put in $24,000. Jill had to invest $72,000. But Jack is the big winner over time when they both hit age 65, right? This is when they're going to retire because Jack made almost $300,000, whereas Jill only made around $250,000. So we can talk money again. We'll do a penny experiment to watch money grow. This is something to think about and look into, ask questions to figure out how to invest your money if you want to retire early, become a millionaire. I once read a story about an Algebra 2 student who kind of learned about exponential growth. They started getting interested, started investing money, I think when they were about 17, 18 years old. And by the time they were like in their 30s, they were a millionaire. So it's kind of an interesting concept, exponential growth. And this works for the decay as well. Things may be going down. Let's explore.